Alright, good morning, Math 125 Statistics. Today we're going to talk about measures of relative standing, section 3.4 in our text, and also talk about box plots today. Alright, I'd like us to recall in chapter 3, section 3.2, we covered measures of center, namely means, medians, modes, and mid-ranges. Then we went on to section 3.3 and talked about measures of variation, range, standard deviation, and of course variance. Alright, what I want to talk about now, measures of relative standing today, section 3.4 enables us essentially to compare apples and oranges. Kind of a catchphrase I'm sure you're familiar with. How do we compare apples and oranges? Well, we'll have measures, a few different measures of relative standing that will be able to tell us numerically the measure of where scores stand relative to each other. Alright, so in section 3.4, measures of relative standing, we're going to cover really four main topics, actually five. We're going to talk about Z-scores, percentiles, and quartiles, and the 5-number summary, and box plots. Right, so those are the topics we will cover today, and these all involve measures of relative standing. How do scores compare one to another? In that regard, let's motivate us a little bit today with a question: which is better? A score of 1490 on the SAT exam, or a score of 17.0 on the ACT exam? Well, you might say we can't know because the scores are taken from two wildly different populations and wildly different score scales on both of these exams. Alright, well, the idea here is we can compare, at least relatively, with a number of tools at our disposal. First one we're going to talk about today is Z-scores. Now, a Z-score is defined as a raw score, which I will symbolize with the variable x, minus the mean of the group divided by the standard deviation of the group. Or if you're talking about populations, of course, we've got the analogous symbols for population Z-scores. So the population mean, of course, would be mu, and the population SD, of course, would be sigma. Alright, so there's our formula for Z-scores, and it's real easy. Just subtract the mean and divide by the standard deviation. The Z-score, well, if you look at it, you should be able to convince yourself it is the number of standard deviations the number of standard deviations a data value is either above or below the mean. Okay, so it's a very powerful formula, very commonly used formula invoking measures of relative standing. If, now let me see if I can get this back in the screen, I think you can see if your x data, your data value, is above the mean, well, this numerator will be positive, of course. If I subtract the mean, then I'll get a positive residue in my numerator. Of course, the denominator is always positive. Standard deviation is always positive. So if x is above the mean, your z-score is always positive. Positive z-scores above the mean. If your data value is below the mean, well, of course, that numerator in the z-score formula will have a negative residue, and that would mean your z-score is then negative. Let me erase that in. Z-score is negative. Right? Positive z-score above the mean, negative z-score below the mean. All right. Let's go back to the SAT example I posed to you. So let's suppose the population mean for SAT scores is 1518. And let's suppose the population standard deviation for SAT scores is 325. Well, let's look at ACT scores. Let's say ACT scores have a population mean of 21.1 and a population standard deviation of 4.8. I'm going to pose that question again. Which is better? A score of 1490 on SAT or let's see, 17.0 on the ACT. Alright, well, if I convert both of these scores to z-scores, remember the z-score will tell me the number of standard deviations you are either above or below the mean. Alright, let's compute the z-score of this 1490 SAT score. I'll take the score, subtract the mean, divide by the standard deviation. Alright, so I'll get my calculator out. 1490 minus 1518. Clearly I'm below the mean here, so I'm going to get a negative z-score. And it turns out I get minus 0.086. That's the z-score of the raw score of 1490 in this SAT body. Okay? Similarly, the z-score for the score of 17 on the ACT. I take the score of interest, I subtract the mean, and divide by the standard deviation. It turns out I get a z-score of negative 0.85. Also a negative z-score. Both these scores are below the mean. Alright, which is better? Well, let's see. Which of these is greater? Alright, please note minus 0.086 is greater than minus 0.85. So I then conclude that the SAT exam of 1490 is better because its z-score is higher. Let me write that down. SAT score of 1490 is better, not because it's greater than 0, or not because it's closer to 0. Some students will say it's simply because of this. SAT score is better because let me erase that. Because its z-score is greater or higher. Okay? Okay. Alright, so that's an easy example of z-score. Let's do another one. And the book cites this example talking about their chocolate chip study stated in the chapter problem, and they ask us which data value is more extreme? Well, extreme means either essentially farther away in terms of standard deviation from the mean. Well, remember the Chips Ahoy study. In our chapter problem, we've got 40 Chips Ahoy cookies. The mean number of chips in these cookies is 24.0. The standard deviation of the sample of 40 cookies is 2.6 in chips. So this was the given data in our Chips Ahoy. Let's see, which data is more extreme? A cookie, let me put it this way, a cookie with 30 chips, and they want us to compare this with a study involving 12-ounce cans of regular Coke. Well, we took a sample of 36 cans of regular Coke, and we're talking about the weight here in pounds of 12-ounce cans of regular Coke. Our sample mean weight from this sample of 36 regular Coke cans was 0.8162 pounds, and the standard deviation was 0.00751 cans. All right, so there's our data from our Coca-Cola study. Which is more extreme, a cookie with 30 chips or a 12-ounce can of regular Coke that weighs 0.8295 pounds? All right. Which of these data values is more extreme? So again, we will compare these cookie versus Coke measurements with z-scores. I'll compute the z-score. Well, remember the z-score. You take your data value, subtract the mean, and divide by the standard deviation. All right, so this is going to be the z-score of the cookie chip value of 30 chips, and we get a z-score of 2.31. All right, what about the 12-ounce can that weighs 0.8295 pounds? Again, we will take our data value under test, subtract the mean of 0.8162, and divide by the given standard deviation of 0.00751. It turns out in this scenario we get a z-score of 1.69 from that data value, and clearly we can see both of these z-scores are positive. That means both the data values are above the mean. So I would claim here the chips value of 30 is more extreme. Well, both the z-scores are positive, so they're both above the mean. It turns out this one gives me a data value that is highest or higher above the mean than the Coke weight of the 12-ounce can. Alright, so two examples of z-scores there. Let's talk about what it means to be unusual in terms of a z-score. Unusual. And our author has set up a somewhat arbitrary scale for z-scores. Now, z-scores can be anything, I suppose, theoretically between negative and positive infinity. The author is claiming if you've got z-scores between -2 and 2, that means your data value is between is within 2 standard deviations of the mean. We call those z-scores ordinary. And if they are either above, if the z-scores are either above 2 or below -2, we call them unusual. Alright, so unusual in ranges above +2 or below -2. The author cites an example here. The author takes his own pulse and asks in an example in the book if the pulse rate of 48 beats per minute is unusual. And clearly the intention here is to get you to compute the z-score of this data value. Well, to compute a z-score, of course, you need a mean and a standard deviation. The author gets a mean and SD from a data set in the back of the book in Appendix Set B that we've seen those in class. Let's see, for the pulse rate in general, from this data set in the back of the book, we're going to assume that the sample mean is 67.3 in beats per minute, and the sample standard deviation from the sample in the back of the book is 10.3 in beats per minute. Alright, so we can easily compute a z-score now. My raw score, my given score under test is 48 beats per minute. Subtract the mean and divide by the standard deviation. Alright, well, 48, that sounds a little low to me for a pulse rate, and if we compute the z-score, we get a negative z-score, of course, meaning that this 48 value is below the mean of 67.3. Well, it's below the mean, but not unusual by our guideline. -1.83 lands me somewhere short of the extreme low range that I set aside for unusual values. So my answer here, not unusual. Okay? Alright, so a few examples of z-scores under our belt. Let's talk about another measure of relative standing, percentiles. Alright, in any data group, there are 99 percentiles, and they are labeled P1, cap P sub 2, ... all the way up to cap P sub 99. And these 99% or 99 percentiles break up the data into 100 groups, each containing theoretically 1% of the raw data. Okay? Example. Simple example. P sub 50. That's our notation for the 50th percentile. And as we might know, if you're scoring in a 50th percentile of a situation, then basically that means half the scores are below your score, half the scores are above your score. Write that down. 50th percentile means half the data is above this value, and half, of course, then is below. Alright, we're going to show you how to compute a percentile value from a data value. Let's see, I'm going to summarize this like this. I'll say, given a data value, let's compute the percentile value, or the percentile score, you might want to call it. Alright, there's a simple formula for the percentile. Percentile of a given data value x is computed according to this formula. It's the number of values less than x in your data set divided by the total number of values times 100. If we look at example 3 on page 115, you may want to pause and go to that data set. I'll turn there myself here. Alright, we see a matrix of values. And again, the author is talking about counts of chocolate chip cookies and 40 Chips Ahoy regular cookies. Alright, we've got 40 data values in this set on page 115. You can see for yourself. And let's say I randomly just select a cookie with 23 chips, and I'm wondering what the percentile value is for those 23 chips. So I'll say find the percentile for a cookie with 23 chips. Okay. So the percentile score, I'll call it, of 23 regarding chips is going to be, well, remember, it's your number of values less than 23. And I can look on my table. Thankfully, this table is sorted, so I can see that I've got 10 values in my sorted list less than 23. And divided by my total number of values is, of course, 40 times 100 will give me my percentile score. Well, 10 over 40 is, of course, 0.25 times 100 is 25. Alright, so the percentile score of 23 chips is 25. So in other words, I can say this statement: the 25th percentile is 23 chips. Right? Another way of saying it, a score of 23 chips in our data set belongs in the 25th percentile. Those statements both are equivalent to that mathematical statement there. Alright, so computing a percentile from a raw score, not very complicated. Here is my formula for doing so. Okay. Alright, now I want to work it backwards. Now in reverse. In other words, I'm given a percentile. I want to find the data value that corresponds to that percentile. Same process we did before, but in reverse. Alright, this going in this direction is a little harder. I'm going to need some notation here because I'm going to have a new formula. Little n. Give me my number of values in my raw data. Little k is going to be the percentile that's given, or the percentile, our author calls it the percentile being used, typically given to us. Cap L is my locator function. What it does, it gives the position of my needed value in the sorted list. Let me write that down. It gives position of your needed value, your sought after value, in the sorted data list. In other words, it tells you where to look. And P sub k, of course, is my kth percentile. Alright, so we're going to use these symbols to establish what we call a locator formula. And remember, locator tells you where to look. in our sorted data list for the answer we seek, and this is the locator formula. It's k over 100 times n, where k is the percentile of interest. Alright, so a little bit of a new formula here. Let me show you how to use this formula. I want to cite example 4 in our text. Example 4 is right on the bottom of page 115. Again, we're talking about the cookie chip data. On page 115, so we want to take a gander at that list. We want to find the 18th percentile in that list. Alright, so we're given a percentile, namely the 18th, and we want to find a raw score, or find a raw data value. Alright, what I'm going to do is use my locator function. L equals k over 100 times n. Well, if I plug in k, remember k is the percentile of interest, it's going to be 18 over 100 times n. N for this data set, you'll recall, is 40. And if I compute L, I get L equals 7.2. Now remember, L is a locator. Tells you where on the list to look for your percentile. Now there's going to be two different rules in this regard, whether L is whole or not whole. All right, let me write them both down here. If L is not whole, what we do is round up L to the next whole number to get P sub k. Let me write that down. We'll round up L to the next whole number to find P sub k, the percentile of interest. So that's how we handle L if L is not whole, but the rule changes a bit if L is whole. If L is whole, meaning a whole number, then the value of the percentile you seek, of the kth percentile, here it's the 18th percentile, is the mean of the nth value and the next up. Okay, that scenario will work out another time. All right, it turns out L is not whole here. L is not whole, so we're going to embrace this instruction here. Okay. All right, so let's finish the example we're given, then we'll do an example where L is whole. Let me get a fresh screen here. All right. You recall that L, we'll write it down again, L was 18 over 100 times 40, and that turned into an L value of 7.2. If L is not whole, we round up L to the next whole number to find or locate P sub k. Here k is 18, right? Alright, so here L is 7.2, so we will round up to 8. 8 is the next closest whole number. So this tells me the 18th percentile is the 8th value up from the bottom on the sorted data list. Okay? Remember, L is a locator. Tells me where to look. Right? Again, if L is not whole, you round up. Here I round up to 8, So P sub 8 is the eighth, P sub 18 is the eighth value. So if I look on my data list, the 18th value on that list is 22. Is it not? 2, 3, 4, 5, 6, 7, 8. Yes, it is. So P sub 18 is 22. Right, so the 18th percentile on that list is 22, and a score of 22 ensures me that 18% of values are below that value. Okay. Same idea. Let's do example 5. Example 5 in our text. Let's see. Find the 25th percentile. Again, still with the chip data. Still referring to the chip data on page 115. Example 5 tells us to find the P sub 25 value, or the 25th percentile. Well, to find a percentile, we need a locator function. And the locator function is your percentile of interest divided by 100 times the number of data values. And remember, what we do with L depends on whether it's whole or not whole. So L is going to be, well, K is 25 here. Remember, K is your percentile of interest. So I sub in 25 for K and 40. Remember, this chip data has 40 elements in it. So, of course, L, it turns out, is 10. And in this example, L is whole. Let me write that comment down here. And if L is whole, right, we say this, that the percentile we seek, namely here the 25th percentile, is the mean of the 10th value and the next value up on that list. So now let me write it like this. The value of the kth percentile, and here we seek the 25th percentile, is the mean of the lth value, which here it would be the 10th value, and the next highest data value. Okay, in general, that's how we handle things when L is whole. Okay, remember here L was 10. Right. So L equals 10. That means the value of the 25th percentile, which is of course the one we seek, is the mean of the 10th value. We'll get that from the list in the middle in a minute. And the next highest. That's all that means. Alright, so I can summarize this with symbols. So the 25th percentile is the mean of the 10th value and the 11th value on my list. So I'm going to write that down as the mean of the 10th and 11th value. Now, what is the 10th value on my list here? 1, 2, 3, it's going to be 22. And the 11th value is 23. And of course, the mean of 22 and 23 is 22.5. So, if L is whole, as it is in this case, the 25th percentile is 22.5. Okay? Alright. Well, a couple of examples of percentiles there. What about quartiles? Quartiles are actually a special case of percentiles, so we'll handle them much the same as we handle percentiles. Well, there are three quartiles, just as there are 99 percentiles. The quartiles are labeled Q1, Q2, and Q3. Well, the three quartiles are values that break up the data or partition the data into four groups, and as you might expect, they each contain 25% of the data. Each containing 25% of data. Alright, I suppose it'll come as no surprise that if I'm looking for the first quartile in any data set, that is of course equivalent to the 25th percentile. 25% of data values are below the 25th percentile. Similarly, the second quartile is the 50th percentile, and another name for that is the median. Remember, the middle score separates the data into half the data below and half the data above the median. The third quartile is of course equivalent to the 75th percentile. So if we are asked to find the quartiles, well, really it's equivalent to asking to find percentiles, which we already know how to do. Let's do an example of same. Let's start out with a real simple data set. Consider this data set here. 1, 2, 2, 9, 11, 12. Alright, this is a 6-element data set. Let me write out here that n equals 6. And I'll ask us here to find the three quartiles, Q1, Q2, and Q3. Alright, I'll start out with the first quartile. As we've already discussed, the first quartile is really another name for the 25th percentile. And I know how to find percentiles. I need my locator function. It tells me where to look in my sorted data list. Alright, so to find the first quartile, well, I want the 25th percentile. Recall the locator function is k over 100 times n. Tells you where to look in your sorted data list. Well, k here, we're looking for the 25th percentile, so k is 25 times n is of course 6. So 25 over 100 times 6 is 1.5. So we get an L value of 1.5, and of course L is not whole. And if L is not whole, we round up. The rule is to round up L to your next whole value. So L is 2. So that means my 25th percentile is the second data value from the bottom, second on the sorted data list. And of course, the second value on that sorted data list is 2. Alright, so the 25th percentile is the data value of 2, and of course that's equal to the first quartile. The first quartile is the 25th percentile. Alright, let's find the second quartile. New screen here. Same data set. As we know, the second quartile is the 50th percentile. And where am I going to look to find that? I need the locator function. Well, here my percentile of interest is 50 divided by 100 times 6 data elements, and that gives me an L value of 3. Now remember, the rule for L whole is a little different here. If L is whole, that means in this case the 50th percentile is the mean of the third value, and the next one up, the fourth value. Alright, so P sub 50 is going to be the mean of the third value on my data list. If I look back at the original data, it's 1, 2, 2, 9, 11, 12. The third value is 2, and the fourth value is 9. And I take the mean of those two, and of course I get 5.5. So the second quartile is the 50th percentile, and of course that's a 5.5. Okay? Let's look at the third quartile now. Well, the third quartile is the 75th percentile. L tells me where to look on the list for that percentile. Well, it's your percentile of interest divided by 100 times 6. And of course that turns into a 4.5. 9 over 2 is 4.5. Alright, L is not whole here. So the rule says if L is not whole, to round up L to your next highest value, next whole value, so that would be 5. So the 75th percentile I seek is the 5th on the sorted data list. And the 5th value on my list, let me write down the data again, 1, 2, 2, 9, 11, 12. 1, 2, 3. The 5th on the data list is 11. So my third quartile, which is indeed my 75th percentile, is 11. Alright. So I found the 3 quartiles for that data. So let me write down summary for this data, 1, 2, 2, 9, 11, 12. Well, the first quartile is 2, as we saw. The second quartile was 5.5, and the third quartile was 11. All right, I want to talk about the 5-number summary. Now, 3 of them are in this list below, and all the 5-number summary is a list of 5 values, namely the min, along with the 3 quartiles, and the maximum data value. All right, that's all the 5-number summary is. So for this data, 1, 2, 2, 9, 11, 12, my 5-number summary will be, well, the minimum data value is 1. The 3 quartiles are 2, 5.5, and 11, and the maximum data value is 12. All right. On test day, I would probably want to label these. So there is my 5-number summary for that 6-element data point I was given. All right, one more subtopic before we call it a day is box plot. Now, don't panic. All the box plot is a graphical representation of the 5-number summary. Now, let me show you how to draw a box plot. I can do it by hand pretty easily here. If I draw a box plot for that data set I was given, 1, 2, 2, 9, 11, 12, well, I'll want the 5-number summary. Write that down again, 1, 2, 5.5, 11, and 12. This is my 5-number summary. Right. What I do to draw the box plot is this. What I'm going to do is create a scale representing the position of those 5 values in the 5-number summary. And of course I'm going to have to start here at the min value of 1, and I'll draw somewhere here the max value of 12. Okay. All right, now I'll plot the second quartile next. That second quartile, well, let's see, is it closer to 1 or is it closer to 12? I think 5.5 is a little closer to 1 than 12, isn't it? So I'll put it about here, and I'll label it 5.5, and that's the second quartile. Now I'll consider the first quartile. Well, 2, is that closer to 1 or 5.5? Clearly it's closer to 2. I'll locate it there and label it Q sub 1. 11. Well, is 11 closer to the second quartile or closer to the max of 12? I believe it's closer to 12 than 5.5, of course. So I'll say 11, and that's equal to the third quartile. And all I do now is connect these values in what I call a box plot. Of course, the book can do a much neater, nicer job of drawing these box plots. And what the box plot does, it gives you a nice relative position of the 5-number summary, as well as how this data is spread out in each of these quartiles. Now remember, the quartiles separate the data into 4 groups, each containing 25% of the data. So it gives you a nice representation not only of the relative position of the quartiles, but also how much is data spread out within those quartiles. Alright, we'll call it a day here, and this concludes section 3.4, measures of relative standing. And that is all.